This is the second module of this week's lectures. We're going to continue with HMMs, understand how the HMM's parameters are estimated and how HMMs are used for acoustic modeling. Okay, let's first do a quick recap. So in the last module, we covered HMMs, and so we essentially laid out the definition of HMMs. What are the simplifying independence assumptions that are made in HMMs, which make lots of these computations much simpler and allows us to factorize various probability distributions in very tractable ways. We looked at two fundamental algorithms with respect to HMMs. So the first is the forward algorithm, which is used to compute the likelihood of an observation sequence given an HMM, okay, which is parameterized as two matrices A and B, where A denotes the transition probabilities in the HMM and B denotes the emission probabilities. And with the second algorithm we looked at was the Viterbi algorithm, which has lots of parallels with the forward algorithm in its formulation. But it's used to compute the most probable sequence of states that are traversed given an observation sequence O, okay, within an HMM, which is parameterized as lambda. So this is the decoding problem. So I'm given a trained HMM and I have an observation sequence. I want to find the most probable sequence of states that was traversed, right, via the observation sequence. All right, so this is where we are. Now in this module, we're going to focus entirely on how we learn the HMM's parameters. So that is, how do we learn the transition probabilities between the states and the emission probabilities at the states, okay, for the observations. So the problem is stated as follows. Given an observation sequence O and the set of possible states in the HMM, meaning that you've already decided what the HMM topology is, okay, how many states it has, how many transitions you're going to allow, and so on. And given these specifications, how do you learn the HMM parameters A and B? Okay, so for this, we look towards the Baum-Welch algorithm, okay, and this is based on a much more general paradigm, which is known as the expectation maximization algorithm. And EM applied to HMMs is the Baum-Welch algorithm. And an interesting kind of fact is that Baum-Welch actually predates the general formulation of EM. So EM is very, very popular in machine learning. But the general formulation of EM was published in around 1977, while Baum-Welch came out in 1972. So this is probably a lesser known fact. So let's first start with trying to understand better what is the EM algorithm. Okay, and then we'll move to how EM can be used with HMMs. Okay, so EM, as I said, is short for expectation maximization. It's essentially an iterative algorithm, and it's used to compute maximum likelihood or maximum a posteriori estimates, but in the presence of hidden variables or unobservable variables. Okay, so here from your ML courses, you all probably know ML estimates and map estimates, right? And in most of those settings, you might have considered all of your data to be fully observable, okay? Meaning that you don't consider that there are some hidden variables in your problem. Okay? So how do you handle such hidden variables or missing data when it exists? Okay, and it does exist in many, many real world settings. So given that you don't have all the observations and there are these hidden variables, how would you go about computing maximum likelihood estimates, right? So let's maybe kind of outline that a little more clearly. So if we have what I'm going to call fully observable data. Okay, so let's kind of denote this using xi's and some zi's. Okay, so there are two random variables. So if you have fully observable data, meaning that for all I, so you have some training set of size n, and you have samples xi and zi, right? Then the log likelihood of a data set, so say you have xi, zi, right, where I is going from some 1 to n. What is the log likelihood? It would be, it's denoted by some L of theta, where theta are your parameters, and it's sum over I log probability of the joint probability of xi comma zi given theta. Yes, so this is the log likelihood. And what is the ML estimate? So your ML estimate is the theta which maximizes the log likelihood, right? And this is the setting which you're all already probably familiar with. Now is the more interesting setting. Say you have partially observable data, okay? That is, xi is observed, but your zi's are hidden. Okay, so you only observe the xi's. So how does this change your log likelihood? Now your log likelihood becomes log probability of xi given theta, because this is the only thing which you have observed. But you also need to take into account the hidden variables, right? You know that these are important when you're modeling your, when you're building a model for the system. So you need to sum over all possible values that this hidden variable can take, right? So here you're marginalizing out these z's, and so then these formulations are equivalent. Okay, so now given this, so let's call this L tilde. So now what is the ML estimate? It's the theta which maximizes this L tilde theta, right? Which is this formulation. And here you have this pesky logarithm of a sum term. Okay, so this is kind of difficult to optimize, right? In kind of a, and how do you do this when Z is not observed? Okay, and this is exactly what EM is used for. Okay, so EM is used to compute, such an estimate, where you don't just have kind of fully observable settings, but you also have hidden or latent variables, okay, for which you don't have observations. All right, so EM is a two-step algorithm. You have an E step and an M step, and it's iterative. Okay, so you keep going through these steps over and over again to estimate better and better model parameters. In the E step, you estimate the hidden variables given the observations and the current estimates of the model parameters. So you start with some initialization of your model parameters, use that to estimate probability distributions over your hidden variables given the observations. Okay, and now you can use these estimates that you have computed in the E step to maximize a likelihood function via which you're going to re-estimate the model parameters, so that now this will be used in the next iteration. okay, for the E step of the next iteration. So here I'm saying estimate the model parameters by maximizing the likelihood function. We are not kind of strictly going to be maximizing the likelihood, but rather an auxiliary function, okay, which is known to be upper bounded by the likelihood function. So I'll go into details of what exactly we'll be maximizing, but this is the two-step iterative algorithm. So in the expectation step, you estimate probabilities of your hidden variables given the observations and the current estimates of the model parameters. So say that it's the nth iteration and you have some theta n, then you find this kind of probability of z given your xi's and conditioned on theta n. Okay, and then in the m step, you estimate a theta n plus 1 by maximizing something which is related to the likelihood function. And here you use estimates that you have computed, the expectations that you have computed in the previous E step. Okay, so this is the overall kind of pipeline. So now let's formally look at the EM algorithm. So say your observed data, we're going to represent as a set of IID samples X size, and you have your hidden data, which is denoted by Z. Now the goal is to maximize your log likelihood. And this, of course, we've discussed, can be further expanded as this logarithm of a sum, right? Because you have these additional hidden variables. All right. So you have a set of initial parameters, which we're going to denote by theta 0. Okay, so the x is observed, z is hidden. You're going to iteratively compute theta L using the following auxiliary function, which we're going to define as q, which is a function of theta and theta L minus 1. So here the note, you're in the Lth iteration. Okay, you're trying to compute theta L, which means that theta L minus 1 are your current best estimates of the parameters from the previous iteration, and theta is the variable. Okay, and this is what the auxiliary function looks like. So you have this q, which is defined as, so let's for a minute forget the outer summation, because the outer summation is just summing over all the training instances. So you only look at the inner summation. It's a sum over all values that the hidden random variable z can take. The conditional probability of z given x and theta L minus 1, which is the previous estimate of theta, times the log probability of the joint of both x and z. Okay, so this is your complete data, right? This is a complete data likelihood, log likelihood. And then this is scaled with this conditional probability over the hidden variables given your observed variables. So once you have this auxiliary function, then theta L is the theta which maximizes q theta, theta L minus 1. Okay, so you might be wondering, I mean, where did this auxiliary function magically come from? Okay, what I ideally want to do is optimize my log likelihood, right? Which is this. Why am I optimizing this auxiliary function? Okay, so I'll come to that in a bit in the next slide. So just assume for now that there's some oracle who has given you this auxiliary function and told you that this is a really good approximation of the log likelihood which you're actually trying to maximize. And this is the formulation. Okay, once you have this auxiliary function, this is the EM algorithm essentially. So the argmax computation is the maximization step, and this Q computation is the expectation step. Okay. And this estimate theta L, one can prove that it does not get worse over iterations, okay, because this particular invariant holds, which is that L theta minus L theta L minus 1 has to be greater than equal to the difference between these two terms involving the auxiliary function. Okay. And because of this is a result which can be proved, for those who are interested, I'm going to point you to some material which will be up on Moodle. But this is optional. Okay, we don't have to understand EM to that extent. I mean, it's not mandatory, but if you're interested, I can point you to material. But what this is saying is that the EM algorithm, so the main takeaway is that the EM algorithm is guaranteed to increase the likelihood so increase or um, stay the same, right? At every iteration, and hence guaranteed to converge. Okay, so that's the main takeaway, that the EM algorithm, this iterative algorithm, is guaranteed to converge because of this particular result. And it's guaranteed to converge, but there is no guarantee of optimality. You can converge at a local optimum or a saddle point. Okay. Um, yeah, so it's guaranteed to converge to a local optimum or a saddle point. And this reference, again, I can point you to this for those who are interested. So let me spend a few minutes. This is again some optional material. You can even so if you're happy to just accept that the auxiliary function, which I showed you in the previous slide, which is this, is upper bounded by the log likelihood, which you truly care about. Okay, and if you're ready to accept that and you don't care about the details, you can skip through this. But for those who are interested, how do we arrive at this auxiliary function? Okay, so let's start with the log likelihood, which is what we truly want to optimize, right? So we want this L theta to be greater. So say that we are at the nth iteration of EM. Okay, so we want, now we are trying to find a new estimate of theta. So we want L theta to be greater than L theta n, right? So it's this. So we want to look at this particular quantity, which is L theta minus L theta n, okay, which can be written as log summation over z probability of x z minus log probability of x theta n. So I just expanded the terms L theta and L theta n, right? So this difference is what I want to maximize. Okay, so I want to maximize this delta, right? So let's kind of write that out here. N is equal to, so log, yeah, so actually before that, yeah, before I actually expand this. So we know that, here you have this log of a summation, right? Minute you see the log of a summation, there's this very handy inequality known as the Jensen's inequality. And in simple terms, what it says is that the log of a summation for weighted sum of xi's is greater than equal to summation over I lambda I log xi. Okay, where lambda i's have to be greater than equal to 0, and sum over all I lambda I has to be equal to 1. This is the Jensen's inequality. Okay, so here I have this log of a summation. So say that, so I need something which looks like these lambdas, these constants lambdas. So I can set that constant to be probability of z given x. Okay, and that will serve as a type of lambda I. So this is So let me say probability of z given x comma theta n, because theta n is already fixed, right, can serve as a lambda. Okay, so now how do I use this to expand this first term, which is the summation over z? So here I'm going to write this out. So let me use Bayes' rule. Okay, so I'm going to write this as probability of z given x. Sorry, not z given x. I'm going to write this as probability of x given z. Okay, times probability of z, right? So that's the joint. And now I'm going to multiply and divide by this quantity which I've determined can serve as a lambda type constant. Okay, so this doesn't change anything. I'm just going to divide and multiply by the same quantity. So now you can apply Jensen's inequality, and you have your constant, which is probability of x given z theta n, and then you have the rest of the terms, right? So log probability of x given z times the probability of z given theta divided by the probability of z given x comma theta n. Okay, and here, of course, you have this additional term, which is the probability of x given theta n. Okay, so you want to choose a theta that maximizes L theta, right? That's the goal. But we've written L theta minus L theta n as being greater than equal to this quantity. Okay, so this large quantity, let me call it some, say, beta function of theta and theta n. Okay, then L theta is greater than equal to L theta n. So it's greater than equal to L theta n plus beta, which is a function of theta theta n, right? So, and this summation, let me call it q. This is the auxiliary function, q theta theta n. Okay, and so now I have that L theta, which is the log likelihood that I care about. It has this auxiliary function, corresponding auxiliary function q, and this auxiliary function is upper bounded by the log likelihood. Okay, so if I cannot easily find a theta that maximizes L theta, it's good enough if I find a theta which maximizes this auxiliary function. Okay, so theta n plus 1, you want it to be the theta which maximizes this auxiliary function. Okay, and this, if you add in the two terms, so beta is this entire large term, L theta n is, we already know what L theta n is, right? If you expand those terms out, you will end up with, it's equal to, you'll end up with summation over all z, probability of z given x theta n times log probability of the joint of x and z given theta. That's it. So now this immediately gives you the two-step EM algorithm. The first step is the computation of this quantity, which is an expectation, right? So it's an expectation of the log probability of the joint of x and z So this is the expectation step, and this is the M step, which is finding the theta which maximizes this expectation. So this is kind of an in-depth. I've not worked out every step, of course, but I can point you to material which works it out. But hopefully you get a feel for why this auxiliary function is meaningful, okay, to optimize instead of the actual log likelihood function. So why go through all this trouble? Because it's hard to optimize the log likelihood function directly when you have hidden variables. And this auxiliary function is much more manageable. Okay, so far we are looking at EM in the general sense. How do we use EM for HMM parameter estimation, right? Okay, so now for that, let's jump right into the Baum-Welch algorithm, for which you will need to track two quantities, which are the forward probabilities and the backward probabilities. And both these quantities will be used to estimate the transition and observation probabilities, okay, in the E step. Forward probabilities you're already familiar with. We've already covered what forward probabilities are in the previous module, right? So that is alpha sub t of j, which is state j, is the probability of having observed O1 to OT and having landed in state j at time step t. That's the forward probability. The backward probability, intuitively enough, is the probability of the future sequence of observations starting from time step t plus 1 all the way to the very end of the observation sequence, which is capital T. So beta sub t of I is the probability of OT plus 1 all the way to O capital T, given that you started in state I at time step t. Okay, so that's the backward probability. Now, much like the forward probability, the backward probability also you can construct a recursion using which you can work it out. Okay, so the recursion look very similar. The initialization is that beta capital T of I is 1. Okay, and then you're kind of computing the backward probabilities all the way until time step 1, right? So in the trellis, you're moving from right to left, and this is the recursive formulation of beta Ti. And the termination is that you find the probability, the likelihood of having observed O as being the sum over all j beta 1 of j, okay, times the probability of emitting O1 at time step j, and the initial times the transition probability, the initial state probability of having started in state j, okay, because you're considering the states at the initial time step. So here's a visualization. So you're here trying to compute beta sub t of I, and in order to compute beta sub t of I, you need access to all the beta sub t plus 1s for every state, okay, in the next time step. This is what I meant by saying that in this trellis, you're going to be computing from right to left, starting from the end of the observation sequence all the way to the beginning. Okay, so now you have both these quantities in hand, which is your forward probability and the backward probability. And in the HMM, what's the goal? You want to estimate how is the HMM fully defined using your transition probabilities and the emission probabilities. I just need an algorithm to be able to estimate both these sets of quantities, right? So first, let's look at how to estimate the transition probabilities. Now, in order to estimate this A sub ij's, we'll need to define this quantity, which I'm going to call psi sub t of ij. Okay, and so let's think of the case where the states are not hidden. Okay, so say that you during training you actually had information about what were the exact state sequences that were traversed by the observation sequences. In that case, we don't need this quantity psi at all. If you wanted to estimate these A sub ij's, I would just look at how many times across all my observations do I transition from state I to state j. I'll make that count and then I'll normalize that count to get a probability, right? The probability of transitioning from state I to state j is the count of the number of times I transition from state I to state j divided by the total number of times that I transition out of state I overall, right? So this is the normalization and I'm done. But what's the problem? The problem is that I don't have access to information about which states are traversed, because these states are hidden. So I don't know what is the state sequence, which is why I need to define this quantity psi, which gives me the probability that at time step t I was in state I, at time step t plus 1 I was in state j, given my observation sequence and the HMM parameter. Now, you need to compute the size of t, and you can compute this probability by trying to compute the joint of divided by the probability of O, right? That's the definition of size of t. And the numerator term, which is this joint over um, qt being I, qt plus 1 being j, and having observed the entire observation sequence, is nothing but the product of four terms, which is the forward probability at state I times the backward probability at state j, and times step t plus 1. And the hop in between, you also have to account for the product of these two terms, which is the product of transitioning from state I to state j, and also emitting OT plus 1 at state j. Okay, because the backward probability beta t plus 1 only accounts from OT plus 2 onwards, right? So OT plus 1 needs to be accounted for, which is what this particular term is doing. Okay, so that's the numerator, which is the joint over these three variables. And the denominator, you have the likelihood, the probability of O given lambda. This I'll leave it as a small exercise for all of you. Convince yourselves that the probability of O can be written as summation over all j, alpha tj times beta tj. Okay, it's just the product of the forward and backward probabilities. So now you have psi t of ij, which is already computed. Now, how do I use this to estimate aij, which is my actual transition probability from state I to state j? Then an estimate of aij is summation over all t, psi t of ij, okay, because over all time steps, you want to sum over this probability of being in state I and transitioning to state j. And then you normalize it. So you divide it by the summation over all time steps and summation over all states that you would have transitioned out of state I. Okay, so here you have psi t of ik. So for all k, you sum over the probability of transitioning out of I, and then you sum over all t, so that you get this normalization term, the denominator, which helps you normalize. So that's the estimate for transitioning from state I to state j. Now, next you want to define you want to look at how to estimate the observation probabilities. Okay? So transition probabilities we already dealt with. How do we estimate the emission probabilities, which is denoted here by B sub j of Vk. So I'm using the notation which is in the reference text, which I have pointed to on Moodle. So there they assume that Vk is some symbol which belongs to some vocabulary V. Okay, so this is some discrete vocabulary. And you assume that Vk comes from that vocabulary. What is the probability of having emitted this particular Vk when you're at state J? That's the emission probability. So first you need to define a new quantity. Let's refer to this gamma sub t of j. Okay, and gamma sub t of j is the probability that you're in j, state j at time step t, given O. Okay, this is commonly also referred to as a state occupancy probability. Okay, so just like we did for the previous psi quantity, just expand this out as the joint over both these terms, which is qt and O, divided by the probability of O, right? And the numerator term is, so this is referred to as the state occupancy probability. These gamma sub t of j is referred to as the state occupancy probability. And the numerator term, which is the joint over qt equal to j and O, is just the product of the forward probability and the backward probability at time step t. Okay, this you can verify for yourselves. And the denominator term, as before, you can write this as kind of summation over j alpha t of j times beta t of j. Okay, so now we have worked out gamma sub t of j. And now to estimate the emission probabilities, which is b sub j of vk, you want to sum over all t's gamma t of j where the tth observation is vk, right? Because we're only interested in the probability of having emitted vk at the tth time step. So here you sum over all t and then look at, wherever OT happens to be Vk, and then compute the corresponding gamma T of J. And the denominator is just the sum over all T gamma T of J, okay, irrespective of what OT is. This is the normalization, right? So here we've now derived an estimate for these emission probabilities as well. So now let's kind of bring it all together. So Baum-Welch, in the previous two slides, we looked at how we can compute the estimates of the transition probabilities and the emission probabilities and some supporting quantities that we needed to define in order to do so. So here, these HMM parameters, we are actually iteratively estimating. Okay, in the E step, we compute these gamma T and psi T quantities. And the M step, we re-estimate the HMM parameters, that is the AIJs and your B sub J of VKs, based on the estimates gamma and psi that you derived in the E step. Okay, so here's the overall algorithm, which is also sometimes referred to as the forward-backward algorithm. So there are many names, all synonymous for the same algorithm, the Baum-Welch algorithm, the forward-backward algorithm, which is used for HMMs. So here in the E step, you compute these two quantities, which is your gamma T and your psi T. Psi T is used to compute the transition probabilities of your HMM, give it to compute an estimate of the transition probabilities, and gamma T is used to compute an estimate of the emission probabilities. And you iterate, keep doing this, right, until convergence. And finally, you return your last set of estimates for both A and B, the matrices A and B. So this is the Baum-Welch algorithm. Now, how do I reconcile what we just saw, the Baum-Welch algorithm, with the EM formulation, that the more general EM formulation that I had introduced at the beginning of the module? So let's try and kind of reconcile both sets of notations. So the observed data, let's say it's Xi's, okay, where I goes from 1 to n. Your parameters, which I was referring to as theta earlier, now it's the transition matrix A and this observation probability matrix B. Now in the E step, these are the quantities which are involved in the computation of the auxiliary function Q. Right? So it's gamma, which is the probability of Zt being J given Xi. So Z is your hidden variable, which is the state, right? The hidden state in the HMMs. And next is your psi IT quantity, which is the probability of being in the jth state at time step t and transitioning to the kth state at time step t plus 1. Right? So this is the E step. And the M step, you want to find the theta which maximizes Q, and you end up with these values. So capital J, A sub JK means the um, index, the row which is indexed by J, and the column which is indexed by K. That particular entry in the matrix is A sub JK, and that is defined as the summation over all T psi ITs, and then you have this outer summation over all i's, which is the summation over all the observations. So before this, we were looking at a single observation O, right? But you can have a number of observations, xi's, where I goes from 1 to n, and so that's what the outer summation is handling. And then in the denominator, you have an additional summation which comes from looking at every transition out of J, right? All right, and then B sub JV is the emission probabilities, that you are emitting V, this simple V in your vocabulary at state J, right? So that is denoted by in the numerator summation over all T, where xit is V. Okay, and then you have the gamma quantities, which you have already defined earlier. Okay, so this is the M step. So this is EM. Okay, so far we've been considering only discrete outputs and derived all these Baum-Welch updates. But we know that HMMs, if they are used in acoustic modeling, the observations that they are going to be dealing with are real valued vectors. So recall, the speech signal is discretized into these small speech frames, and corresponding to each speech frame, I have a vector of real valued numbers, right, which denotes my acoustic feature vector. And these are my observations, because they're no longer these discrete outputs, which means my observation probabilities are not going to be like multinomial distributions, but instead I need to be considering density functions, because I'm dealing with continuous outputs, right? So I have to use probability density functions to define my observation probabilities. So if I were to think of my observations as just being 1D values. So it's not vectors of some of size. They're not vectors of d-dimensional size, but they're just 1D vectors, right? There's just a single value corresponding to each speech frame. Then my observation probabilities B sub j of x, I can think of them as being modeled as a Gaussian, okay, a univariate Gaussian, where mu j is the mean associated with state j and sigma j square is its variance. But typically my x's are not 1D, but they actually are d-dimensional vectors of real values. Right? Then we need to use multivariate Gaussians. It's not univariate Gaussians. So now you can write b sub j of x, where x now is this acoustic vector. I can write it as a multivariate Gaussian, where mu j is the mean vector of size d associated with state j, and sigma j is the covariance matrix associated with state j. Okay? Like, so this is how it would be parameterized if they are multivariate Gaussians. All right. So now, what would Baum-Welch look like if I have Gaussian observations, right? So my parameters. What are now the parameters of my HMMs? The transition matrix stays the same. I have these transition probabilities going from one state to the other, but my observation probabilities now are no longer, this big matrix B, okay, where I can enumerate all the symbols from my vocabulary, which was the case when I was dealing with discrete outputs. But now that I have these continuous outputs, which I'm saying are parameterized using various Gaussians, okay, and they're parameterized by mu j and sigma j for all j. So each state j has a different multivariate Gaussian associated with it. Okay, so then estimating B, the observation probabilities, would amount to estimating all the mu j's and sigma j's for all states j. So that's the main change now that I'm dealing with Gaussians. So A is the same. Now I say that I go through EM. A is estimated exactly the same way as with discrete outputs, but now with my continuous outputs, I need to estimate mu j and sigma j. And how do I do that? So here mu j is, I'm looking at one entry in the mu j mean vector. This is capital mu j. And here I'm looking at one entry. Here you can, so it's essentially sum over all xit. Okay, the outer summation, this is for completeness sake, just to make the notation simpler to understand. You can even not worry about this outer summation at all. The summation over I, just look at the rest of the terms. So here you have a summation over t, gamma t of j, I comma t of j times xit, okay, divided by the summation over t gamma it of j. So here so what is this saying? You're finding the essentially the weighted mean of xits, right? And the weights are these state occupancy probabilities, which is my gamma IT. So recall intuitively, what is the state occupancy probability telling you? It's the probability that you're in a particular state given the observation, right? So if I'm looking at mu j, um, I can't just uh, uh, I can't just take the average of all XITs, but I need to scale it with the probability that it could have been omitted at state j. Right? So that's what this particular state occupancy probability is giving me. And similarly, to compute the covariance matrix sigma j, in the numerator term, you'll notice this is the familiar expression which is used in kind of covariance matrix computations. But additionally, you have the scaling with the state occupancy probability. Okay, because this is telling you this is the probability of being in state j. So far we assume that the observations could be parameterized using a single multivariate Gaussian distribution. But this turns out to be very simplistic because a single multivariate Gaussian is unimodal. And so this kind of restricts the expressiveness of the underlying probability distributions that we can use for the observations, our acoustic observations. Okay, so we use a more powerful parameterization for the emission probabilities, and we use what are called mixtures of Gaussians. Okay, these come from a larger set of models referred to as mixture models. Just think of mixture models as being a mixture of components where each component is parameterized in the same way. So here each component is a Gaussian, and then we have a mixture of Gaussians. Okay. And this is it's much more powerful. So if you consider say like a simple example where you have, so let's consider the univariate case. Okay, so you can visualize this. Say that you have one univariate Gaussian, which looks like this. And then say you have a second univariate Gaussian, which looks like that, right? Then a mixture of these two Gaussian components would look something like this. Okay, something like that. So you see that it's bimodal, right? Which is much more expressive than each of these individual components, which are unimodal. And so you can increase the number of mixture components, and then that will help kind of model lots of very non-trivial shapes that the probability distributions can take. So these mixtures of Gaussians are much more powerful, and they turn out to be sufficient to do a good job of parameterizing our acoustic vectors. So now, how does this change the expression b sub j of x? So instead of b sub j of x being a single multivariate Gaussian, now it's a mixture of Gaussians. So now b sub j of x is a summation over m. Here, the small m is indexing the number of mixture components in your mixture. So it's this c sub j of m times a Gaussian PDF, right? A density function where now you have a mean vector for every mixture component m corresponding to state j, and you have a covariance matrix for every mixture component m in state j. Okay, and now you also have these additional mixing probabilities. This is the probability with which you're going to prefer one of these mixture components, which is indexed by m. And so summation over all m CJM should be 1, and each CJM will be greater than equal to 0 because it's a probability. Okay, so now you have these additional mixing probabilities as well, along with the means and covariance matrices associated with each mixture component. So now going back to Baum-Welch, you have for each state j, you have not just a single mean vector and a covariance matrix, but you have m mean vectors and m covariance matrices, and you also have these mixture probabilities. Okay, so these all have to be estimated as part of the Baum-Welch algorithm. So now here mu Jm and sigma Jm are similar to what we saw in the case of multivariate Gaussians, except now these occupancy probabilities, gamma, are also kind of functions of M, right, the mixture component. And CJM is, you only look at the, again, you just compute the state probabilities, the state occupancy probabilities, you sum over all T and I, and you divide by the summation over all mixture components, which is denoted here by M prime in the denominator. So here, so all of this, all that we have seen so far, please spend some time kind of reading the material that I'll post on Moodle, and then actually looking at each of these expressions and making sure that you understand how each of them are kind of derived. Yeah. All right, so here's a summary of Baum-Welch. So these are the entire set of parameters that we want to estimate, where these are your transition probabilities, and then the emission probabilities are parameterized using mean vectors for every mixture component in every state, covariance matrices again for every mixture component in every state, and then you have these mixing probabilities, which are denoted by C sub Jm, okay, for every state J again. Okay, so now let's give a kind of bird's eye view of how all of this ties together. What all the, in the last module and this module, the HMM algorithms that we covered. So during training, you start with the speech signal, discretize it. Now you have a sequence of acoustic feature vectors denoted by O sub 1 to O sub T1, where T1 is the length of the sequence. And the superscript denotes that this is the first observation sequence. And you have a corresponding word sequence denoted by W1 to WL1. Similarly, you have n different observation sequences and corresponding word sequences. So this is your training data set. Now you need to estimate theta over all the phone states. Okay, so now you have HMMs corresponding to each phone, and each of those HMMs will have, say, 3 or 5 states for each phone. And these are the details which I'm going to cover in the next module in a lot more detail. And they'll all have corresponding parameters which you're going to estimate using Baum-Welch. Now the HMM of the ith training utterance is determined by using a word to phone mapping first, which is applied to the corresponding word sequence denoted by W1 to WLI. Okay, so this is how an HMM, so you can think of this as a mega HMM, where you have these tiny HMMs corresponding to each phone, right? And then you string together all of these HMMs to put together this large HMM corresponding to the entire training utterance. Okay, and these are the HMMs. You can train the language model separately using just the word sequences. And now during test time, you have a new observation sequence, and you want to find the W which maximizes this conditional probability. Now this you're going to compute using the Viterbi algorithm. Okay, you want to search through all possible state sequences, okay, which arise from some word sequences, which are most likely to have generated O. Right? So given O, what is the most likely state sequence that I could have traversed? That is exactly what the Viterbi algorithm gives me. But this turns out to be computationally intractable to do in an exact manner. Okay, so exact inference. So doing Viterbi exactly turns out to be computationally intractable. And so there are kind of approximations which we will cover in more detail when we look at the search algorithms and the decoding algorithms which are involved within large-scale ASR systems. Okay. So with that, this is the end of this module. And in the next module, we will revisit the training of HMMs for acoustic models. And then we'll go through some important design choices which are made in order to improve the accuracy of these HMMs, okay, specifically for ASR.